Hi, this is HAO HAO. Welcome to the presentation of music FaderNets. High-level musical features like emotion and style are abstract, hard to quantify, and often require human annotations. However, training conditional models on these human annotated labels might give bad results, either because the labels are insufficient or because the labels are too noisy due to human subjectivity. To solve this, we propose to use low-level features as a bridge, since high-level features are intrinsically related to a set of low-level features. For example, arousal can be closely related to rhythm and note density. By tweaking the levels of rhythm and note density in a constrained manner, we can achieve a desired change on the arousal level. We call the controllers of low-level attributes faders, and the relationship between faders and a high-level feature are known as presets. With the analogy above, we name our framework as music FaderNets. Faders are learned with latent variable models, whereas presets are learned with Gaussian mixture VAEs, as it imposes a hierarchical structure to infer high-level clusters from low-level latent vectors. This is the model framework of music FaderNets. It consists of 4 components. The encoding component encodes the input polyphonic music, which has been converted to event-based tokens. Each encoder governs the posterior distribution of a feature latent space. As we want to incorporate the fader behavior, one of the dimensions is regularized, meaning to map the value change to the change of the output musical feature. We experimented with several regularization techniques and conclude our results in the later slide. The discriminator component enforces the latent vector to incorporate information of the assigned low-level feature. The training objective is to reconstruct the low-level feature label, for example, a sequence of rhythm event labels, and etc. This can be trained via supervised learning because labels are abundant. The cluster inference component infers high-level features from low-level latent vectors. For example, it tries to infer arousal labels from the rhythm and note density vectors. As human annotations are scarce, this can be trained using semi-supervised learning using Gaussian mixture VAEs. Finally, the reconstruction component reconstructs the original token sequence from all latent vectors in an autoregressive manner. To evaluate our model, we want the low-level faders to be independent of each other and changes linearly with the output musical features. This gives rise to 3 metrics, namely consistency, restrictiveness, and linearity. Our experiment shows that among all 4 existing methods, Party et al. Has the best overall performance, and especially superior in terms of linearity, which is very important for the fader behavior. Hence, we adopted their approach in our model. For the cluster inference component, we see that high arousal is learned to relate to high rhythm density and low note density, while for low arousal it learns the opposite. Both are very reasonable because music with high arousal often consists of fast-running single notes, whereas music with low arousal often exhibit a chordal texture with more sustains. Interestingly, this relationship is learned with only 1% of human annotated arousal labels, which means our framework is capable of learning even under weakly supervised conditions. Furthermore, we can achieve arousal style transfer by constructing a style shifting vector from the mean point of one Gaussian mixture to another. During decoding, we can apply the shifting vector on the encoded latent variable, and the decoded output should exhibit a different arousal style. This effectiveness is further confirmed by a subjective listening test, which suggests that this method can be useful for style transfer on abstract features. To summarize, we present music FaderNets, which is a model framework for controllable music generation based on abstract high-level features. First, we use faders for low-level features with latent variable models. Then, the presets are inferred using Gaussian mixture VAEs, which proves to work even under weakly supervised conditions. Finally, we can also achieve style transfer with shifting vectors, and we demonstrate an example on transferring arousal. Thank you, and hope you enjoy this presentation.